The definite integral, by definition, is the limit of a Riemann sum. And I'm going to explain this example that's here, and then we'll do some of the exercises that are below it. This definite integral, the integral of x to the fifth dx from 1 to 5, when x is 1, x to the fifth is 1, and when x is 4, x to the fifth is 4 to the fifth, which is up here somewhere. And there's some curve that passes through these points. Doesn't really matter how accurate this graph is. So the integration is starting at 1 and ending at 4. The integral means the area between the function and the x-axis from x equals 1 to x equals 4. So we're going to make right rectangles for all of these problems, right rectangles. The width of each rectangle is always b minus a over n. B is 4 and a is 1. B minus a over n. N is the number of rectangles. That's 3 over n. So the first rectangle starts at 1, and it's going to be that number 1 plus whatever the width of a rectangle is. And we're going to go from here to the point on the graph to make a right rectangle. This next rectangle is going to be the x where we started plus the width times 2, because it's the second rectangle. The second right rectangle, and so on. The next rectangle's going to end at 1 plus 3 times 2 over n, and so on. In general, any rectangle this point at the right side is going to be 1, which is the x we're starting at, plus k times the width of each rectangle. Where when I say k, I mean this rectangle is the kth rectangle. When we take 3 over n times 1, we'd have what's called the first rectangle. I meant to say we take 3 over n times 1, that's what's here for the first rectangle. When we have 3 over n times 2, the 2 is because that's the second rectangle. So in general, if this is the kth rectangle, this point right here on the x-axis is 1, because we started at 1, plus k times 3 over n. So the y-coordinate of this point, since this point is on the function, is whatever x is to the fifth, where this is x. So the y-coordinate of that point is whatever x is here to the fifth, because this graph is y equals x to the fifth. Y equals x to the fifth. So the y-coordinate is 1 plus 3k over n to the fifth. And that actually, what I just wrote, is the height of this rectangle. I'll just write it again over here. 1 plus 3k over n is the height, or how tall the rectangle is. I mean 1 plus 3k over n to the fifth. The y value there is the height. The width of the rectangle is 3 over n, because every rectangle here has the width 3 over n. The length times the width is the area. So this would be the area of every rectangle. We put a sigma here, meaning we're going to add them all up from k equals 1, that's referring to this first rectangle, all the way up to um, n, where n is how many rectangles there are. And if we make the number of rectangles infinity, if we make them all so skinny that you can fit infinitely many of them, we would need the limit of that sum as n approaches infinity, which is exactly what's here. The limit of this Riemann sum as n approaches infinity, that's what that's supposed to say, is the same as this definite integral. So just notice that if k is 1, this thing right here becomes that to the fifth. And if k is 2, this whole thing right here becomes all that there to the fifth, and so on. So the k means we're just talking about any of these rectangles, not just the first one or the second one or the third one. This refers to any of them, starting with k equals 1, the first one, up to the nth rectangle, where we'd like to make n infinitely many rectangles. So that's the example explained. The example has the question with the answer next to it. So there's all these exercises down here. I'll do a few of these with you. Let's do number 2. What we're the directions are to write this integral as the limit of a Riemann sum. So that's 2 is the number of the problem. So this is some general function f of x. So if here's the y-axis and here's the x-axis, at x equals 1, from x equals 1 to 5, the function is whatever. The integral means the area between this function and the x-axis from x equals 1 up to x equals 5. So if we cut this up into right rectangles, the width of each rectangle has to be b minus a over n. B is 5 and a is 1. N is however many rectangles we need. So the width of every rectangle is 4 over n. That means the first rectangle is going to start at 1, and it's going to go to that number there is going to be the starting x value plus the width. There's a rectangle. The next rectangle will end here, which the x coordinate there is going to be whatever the starting x value is, plus twice 4 over n, and so on. In general, any rectangle, the end of it, the right side of it, I should say, will have an x coordinate 1 plus k times 4 over n. Where k means, well, if k is 1, I'm talking about where the first rectangle ends. If k is 2, I'm talking about where the second rectangle ends. When I put a k there, I mean I'm talking about where any of the rectangles end. That's the kth rectangle. The y coordinate of this point is whatever y is on this graph. Well, everywhere on this graph, y is f of x. So the y coordinate there is f of whatever this x is. It's 1 plus 4k over n. So f of this x value is actually the height of the kth rectangle. F of 1 plus 4k over n is the height of this rectangle. And the width of this rectangle here, the width of every one of these rectangles is 4 over n. So we have the length times the width, that's the height times the width, which is the area of any one of these rectangles. We put a sigma so we could add up the areas of all the rectangles from k equals 1. That means from the area of the first rectangle up to the nth rectangle, and then just make the limit as n approaches infinity. Lim n, meaning how many rectangles there are. We'll make that get as big as we can. Infinitely many rectangles will make them very, very, very skinny. So what's written in here in red is equal to this definite integral. The limit of this sum as n approaches infinity means the same thing as this integral. Okay, let's try number 4. Okay, this time we have the limit of the Riemann sum, and we have to come up with the integral. So based on the examples we've already done, that would be the x value where the function is starting, because it's always the a value plus something. So the function is starting at 0, because I can see that. And I'm going to guess that it's the cosine graph and then verify the guess. So cosine graph looks like this. And an integral always means the area between the whatever the function is and the x-axis from some starting x value up to, I'm not sure what the n value is. We'll talk about that in a minute. So the first rectangle is going to start at 0, the first rectangle, and go be somewhere here. These are always going to be right rectangles. Well, I can tell by the form that the width of each rectangle is this fraction, but the width of every rectangle is always b minus a over n. So this thing, it must be the b minus a over n. That means b minus a has to equal pi, because if the denominators are the same, the numerators must be the same. And we decided that a is this number here. Okay, I meant to say b minus a equals pi, because, like I said, if the denominators are equal, the numerators must be equal. A is 0. B equals pi. So we're going to say it's the integral from a, which is 0. So now we know b is pi. And we're going to put cosine x here. And that's like the dx. And that's it. If we work backwards, we'll see why this is right. The thing in the red circle is the answer, because cosine x looks like this. If we start at 0, and go to pi, these are all the rectangles. So if this was given, I'd say delta x is b minus a over n, which would be pi minus 0 over n, which means this rectangle, or this point here on the x-axis, would be the starting x plus pi over n. The next one would be the starting x, which is 0, plus 2 pi over n, and so on. In general, any rectangle's right side would end up at the starting x plus k pi over n. And then we'd say the point, this y-coordinate here, if this is the function, the y-coordinate would be the cosine of this x value, the cosine of k pi over n. That makes that the length or height of this rectangle, cosine k pi over n. And the width of each of these rectangles is pi over n. And here, so the length times the width is the area. Add all of these up from k equals 1, meaning the area of the first rectangle, up to n, meaning up to the nth rectangle, however many there are. And then put limit as n approaches infinity in front of it, and we have exactly what we started with here. I know you can't see the 0 here. K pi over n. Yep, it's all matching. I just didn't write limit yet. Let's try number 6. All right, so you need the picture. Y-axis, x-axis. When x is 4, y is whatever. When x is 5, y is something else. So we got this function. Doesn't matter really what it looks like. The integral means the area between this function and the x-axis from x equals 4 to x equals 5. We slice this up into right rectangles. There's the first rectangle. There's the second rectangle. And so on and so on. Here's the kth rectangle. We're going to make the width of each rectangle b minus a over n. B is 5 and a is 4. N is the arbitrary number of rectangles. So 1 over n is the width of each rectangle. That means this x-coordinate is 4 plus the width. This x-coordinate, or this x value on the x-axis, is 4 plus 2 times 1 over n. 4 plus 3 over n, and so on. If I'm at the kth rectangle, the x I'm pointing to here is 4 plus k times 1 over n. So that's the x-coordinate. Go up here to the graph. The y-coordinate here is whatever x is plus 1 squared. The y-coordinate here is whatever x is plus 1 squared. And that is how tall this rectangle is, what I just wrote there. I could write that as, I'm going to leave it like it is, 4 plus k over n plus 1 squared. And the width of this rectangle, the width of every rectangle, is 1 over n. Length times width, that's the area of this kth rectangle. If you make k1, it's going to be the area of this first rectangle. Make k2, all of this will be the area of the second rectangle. So we sum all of those areas from k equals first rectangle to nth rectangle, however many there are, and then make the limit as n approaches infinity. And this should be the answer to number 6. Let's see if we can do number 8. Okay. Okay, so I'm going to guess that the function, I'm doing a little guessing here. I'm going to guess that the function is 3x plus 2. And that's going to be the starting x value. I'll explain all this in a minute. So starting at x equals 4, I'm not sure the ending yet, but I'm guessing the function is 3x plus 2. And then this is the dx, or the width. So to get the number here, I'm going to say delta x equals b minus a over n. I'm guessing that delta x is this fraction. I sort of guess that that's a. A is 4. Since these denominators are equal, they're both n's, the numerators must be equal. B minus 4 must equal 1. So I'm going to add 4 to both sides. So I believe this is the answer to exercise 8. The integral from 4 to 5 of 3x plus 2 dx. And you should work this backwards to verify that that's right. So due to this integral, what we just did to number 6, if we start with the integral, we end up with the limit of the Riemann sum. So try that with number 8. Try that with the answer to 8. See if it turns into the limit of this Riemann sum up here. And let's do number 10. So, to find the a value, well, first of all, I'm going to guess again that this function is cosine x, and then that's dx, the pi over 3n. So a little bit of guessing here. I'm guessing that this limit represents the integral of cosine x dx. And to find the a value, I always look for something with pi over n in it added to a number. So I'm going to assume there's a 0 plus there. So 0 is the starting value. And the fraction that has n in the denominator is usually delta x. Maybe it's always that, b minus a over n. So I'm thinking this thing I'm circling here, pi over 3n, is the delta x, b minus a over n. The problem is these denominators are not equal like they've been in the other examples, so maybe we should multiply the top and bottom of this one by 3, because that won't change. I'm going to change this numerator to 3b minus 3a. If we multiply the numerator by 3, we have to multiply the denominator by 3. Now I can say, since the denominators are equal, these numerators, 3b minus 3a, and pi must be equal. And we made an educated guess that a is 0, because there's nothing added to this fraction. So if a is 0, we get 3b equals pi, if a is 0. So b, which is the number that goes up here, is pi over 3. And that's it. So to verify that that's right, let's try turning this integral into the Riemann sum. Cosine x graph starts at 1 up here and then goes down and so on. If we are talking about the integral of this function from 0 to pi over 3, the first rectangle would start at 0, because that's down there, and end somewhere. And the ending place is always delta x, change in x, which is always b minus a over n. So if this answer is correct, then B is pi over 3 and A is 0. So we have pi over 3 minus 0 over n. And if we multiply the numerator and denominator by by 3, we get pi over 3n. That means this x value is the x where we started, which is 0, plus pi over 3n. 1 pi over 3n, because that's the ending of the first rectangle. Second rectangle would be 0 plus 2 pi over 3n. Third rectangle would be 0 plus 3 pi over 3n, and so on. In general, any rectangles, a right endpoint would be, we have an x value of 0 plus k pi over 3n. And that number there is the x coordinate here. And so the y coordinate, where this touches the graph, if this is the function, it would be the cosine of whatever x is. It's the cosine of this k pi over 3n. And that would have to be how tall this rectangle is. Cosine k pi over 3n is how tall the rectangle is. And this is how wide any one of these rectangles is, pi over 3n. Length times width, that's the area of this kth rectangle. If k is 1, right here, that would be the area of this first rectangle. If k is 2, it would be the area of the second rectangle. So we say sigma, k equals 1 up to n, meaning however many rectangles there are, and then make the limit as n approaches infinity. And this is actually what we started with. Just check it. Limit. Just making sure that what we started with is what's down here. K pi. It looks like a match to me. So the answer to exercise 10 is this right here.